Excitement surrounded the long-awaited activation of the most advanced high-energy particle collider, a development years in the making. The Large Hadron Collider (LHC), constructed by the European Organization for Nuclear Research (CERN), became operational in September 2008 after an extensive construction phase. However, it took several more years for its creators to fine-tune the machine. Since then, the LHC has played a crucial role in unraveling various mysteries of the universe during its numerous experimental runs. Yet, recent developments have raised concerns among scientists at CERN. After ramping up the LHC to its highest energy levels, researchers observe something surprising and unsettling. Further investigations have led to multiple theories attempting to explain this anomaly, but no conclusive answers have emerged, leaving it speculative for now. The universe is filled with countless unexplained mysteries, and over the years, scientists have dedicated their time to studying and understanding some of these phenomena. These include the enormous black holes in space, which possess such strong gravitational forces that even light cannot escape them, and the Bermuda Triangle, known for mysterious disappearances of ships and planes. Many of these phenomena remain unsolved due to limitations in technology. In the early 20th century, physicists sought new methods to explore the fundamental building blocks of matter. In 1932, physicists John Douglas Cockcroft and Ernest Walton created the first functional particle accelerator. These particle accelerators are essential tools for investigating the fundamental components of matter by accelerating particles to high energies and colliding them, allowing researchers to study the subsequent interactions and test the fundamental forces and particles that make up the universe. Given the usefulness of particle accelerators in explaining cosmic mysteries, CERN built the world's largest particle accelerator. However, researchers have recently made a troubling discovery, suggesting that this powerful machine might be capable of triggering the Mandela effect due to its ability to alter the fabric of space and time. What does this discovery mean? Many people wonder why they remember events differently from how they actually occurred. This phenomenon, known as the Mandela effect, was first identified in 2009 by Fiona Broome. She and many others mistakenly believed that Nelson Mandela had died in the 1980s, when in fact, he passed away in 2013. Various factors contribute to this effect, such as false memories and the strong influence of social media and the internet. However, some researchers have raised concerns that previous operations of the LHC might have contributed to the Mandela effect, a theory not yet proven. Before dismissing this idea as a conspiracy, it's important to note that prominent scientists and public figures have expressed concerns about the potential dangers of the LHC. Stephen Hawking was one of the first to warn about the risks, stating that the collider could create black holes that might threaten the universe. Dr. Carlo Rubbia also voiced concerns in a blog post, suggesting that the LHC could produce exotic particles capable of transforming surrounding matter into something entirely new. Renowned figures such as astrophysicist Carl Sagan and science fiction writer Arthur C. Clarke also raised alarms, speculating that the collider could create strangelets or even cause a black hole to swallow the Earth. In a press conference, President Obama also expressed concerns about the collider potentially causing a catastrophic event that could alter the very fabric of reality. The fact that multiple groups, from scientists to writers to public figures, have expressed unease about the LHC highlights the gravity of these concerns. While the outcomes remain unpredictable, it's important to carefully consider the potential risks and make informed decisions regarding the collider's operation. Could the LHC really be capable of triggering the Mandela effect and other changes in our universe? The LHC, currently the world's largest and most powerful particle accelerator, was built between 1998 and 2008 with a collaboration of over 10,000 scientists from more than 100 countries. It became operational on September 10, 2008, as the latest addition to CERN's accelerator complex. The LHC's primary goal is to test predictions from various theories in particle physics, including investigating the properties of the Higgs boson, searching for a multitude of new particles predicted by supersymmetry, and exploring other unresolved questions in particle physics. The collider is a 27-kilometer ring built with strong materials and structures that accelerate particles to incredibly high speeds before directing them into collisions. These beams of energy particles travel in opposite directions through separate tubes called beam pipes, which are kept at a very low pressure. The pipes follow a circular path around the collider due to a strong magnetic field generated by superconducting magnets. These magnets are made of coils of special electric cables that function in a superconducting state, allowing electricity to flow without resistance or energy loss. To maintain this superconducting state, the magnets must be cooled to a temperature of -271.5 degrees Celsius, colder than outer space. To achieve this, liquid helium is used to cool the magnets, alongside other essential air supply services throughout the accelerator. Operating at an energy level of 6.5 TeV, tera-electron volts, per proton, the LHC accelerates protons from 450 GeV, gigaelectron volts, to 6.5 TeV. During this process, the magnetic field of the superconducting dipole magnets increases from 0.54 to 7.7 teslas. The impact energy of the protons reaches an impressive 13 TeV, and they achieve a velocity close to the speed of light, about 0.99999 times the speed of light. A proton completes a full circle around the LHC ring in less than 90 microseconds, resulting in an astonishing 11,245 cycles per second. The proton journey at the LHC begins in a linear accelerator, LINAC 4, which generates negative hydrogen ions at 160 MeV, million electron volts. These particles then travel through the proton synchrotron booster, where electrons are stripped away, leaving only the nuclei to proceed through the accelerator. Several hypotheses suggest that a central nuclear field, such as the Higgs field, could be responsible for certain phenomena. The future and nature of our planet have become subjects of intense investigation because, according to the standard model of particle physics, there is a possibility that the universe's vacuum state could persist for a significant amount of time but remain inherently unstable. This suggests that the universe could eventually stabilize, fundamentally altering our understanding of reality. The stability of the vacuum that underpins the universe is significantly influenced by particles like the Higgs boson and the top quark. If the universe exists in an unstable vacuum, it could lead to dramatic changes in the distant future. This raises the need for precise measurements of the top quark's mass, which can be determined using a unique particle collider known as the electron-positron collider. By studying this, scientists hope to predict what might happen if the vacuum stability were to change over time. Researchers also believe that the Higgs field, which fills the vacuum, played a key role in shaping the early universe by influencing its energy during its first moments. This idea proposes that the Higgs field has undergone various changes over time, contributing to the fundamental forces we observe in the universe today. Currently, scientists are investigating the relationship between the Higgs field and the energy in the universe's void. The energy in space right now is nearly zero, yet theories involving the Higgs field suggest that it should be much higher, presenting a significant challenge in physics known as the cosmological constant problem. Looking back at history, we can see how particle physics has evolved to help us understand the basic building blocks of matter and forces. In the 1960s, scientists struggled to unify the electromagnetic and weak nuclear forces using quantum field theories. Their models, such as the Young-Mills theory, predicted that certain particles which we knew had mass should actually be massless, creating a major issue. Another theory, Goldstone's theory, proposed the existence of massless particles called Goldstone bosons, adding complexity to the problem. Initially, these ideas were not well received, but later advancements by physicists like Peter Higgs and others in the 1970s played a crucial role in resolving these challenges, eventually transforming these theories into well-established parts of modern physics. The discovery of the Higgs boson and the exploration of its role in the universe have led scientists to investigate its potential impact on the stability of the universe and the vacuum energy. The Higgs field is central to understanding these phenomena, from its involvement in the Big Bang to its influence on the forces that govern everything in the universe. Researchers are currently studying how the Higgs field interacts with the universe's vacuum, particularly since the energy levels within empty space today are extremely close to zero. The Higgs field theory suggests that this energy should be much higher, contributing to the ongoing mystery of the cosmological constant problem. In the early 1960s, researchers faced major hurdles in trying to create a unified theory of particle physics that included both the weak nuclear force and electromagnetism, particularly when using gauge theories. The discovery that W and Z bosons, particles involved in the weak nuclear force, have mass contradicted earlier predictions that they should be massless. This discrepancy led physicists to consider new possibilities, including the potential existence of Goldstone bosons, although there was no solid evidence for these particles. This left the scientific community with a dilemma. Was the gauge theory flawed, or was there some unknown factor giving mass to the W and Z bosons without producing Goldstone bosons? In the 1950s and 1960s, researchers struggled to solve these problems, and there was no comprehensive theory of particle physics. The discovery of hadrons, composite particles made of quarks, has been vital in understanding the interactions between fundamental particles, especially in extreme conditions. By studying hadrons at facilities like the Large Hadron Collider (LHC), scientists have made significant progress in refining the standard model of particle physics, though many mysteries remain. The standard model explains much about how the universe works, but it does not address key questions, such as the nature of dark matter and why there is more matter than antimatter in the universe. The study of the Higgs boson has opened new avenues for particle physics, allowing researchers to probe the universe's most fundamental components. As scientists continue to study the Higgs boson, they hope to uncover insights that could help resolve some of the outstanding issues in physics and potentially advance our understanding of the universe itself. If researchers can better understand the Higgs boson, it may lead to groundbreaking discoveries, driving forward the field of theoretical physics and offering new perspectives on the fundamental forces of nature. While the LHC is an immensely powerful tool for exploring these cosmic mysteries, it's important to note that there is no scientific evidence linking it to phenomena such as the Mandela effect or the creation of black holes. The LHC's role in unlocking the secrets of the universe remains significant, but it's crucial to avoid speculative and unsupported claims. The LHC is a vital technology that could help us understand the universe and the planet we live on, but we must be cautious about drawing conclusions without sufficient evidence, as doing so could have unintended consequences. In the particle accelerator process, protons are first accelerated to 2 GeV before entering the proton synchrotron, where they reach an energy of 26 GeV. The superproton synchrotron then boosts their energy to 450 GeV before injecting them into the main ring. In this ring, protons are further accelerated to their peak energy over the course of 20 minutes, circulating for 5 to 24 hours to allow for collisions at 4 intersection points. While proton collisions are the primary focus of the LHC physics program, dedicated periods, usually several months each year, are reserved for heavy ion collisions. Lead ions are the preferred particles for this program, and they are accelerated to an energy of 2.3 TeV per nucleon or 5.02 TeV per particle in the LHC ring. The LHC operates with enormous amounts of energy, consuming significant power and generating vast amounts of data, highlighting the scale and importance of the scientific effort. CERN draws about 200 megawatts of electrical power from the French grid during LHC operations, roughly one-third of the energy consumption of the city of Geneva. Notably, the LHC's accelerator and detectors consume about 120 megawatts of this energy, surpassing the energy demands of the relativistic heavy ion collider, RHIC. The heavy ion program aims to explore quark-gluon plasma, a state of matter believed to have existed in the early universe, providing crucial insights into the fundamental nature of matter and the universe. A major milestone of the LHC was the discovery of the Higgs boson, a particle central to the standard model of particle physics, in 2012. This discovery was crucial in confirming the existence of the Higgs field, a theoretical field proposed by Peter Higgs and others in 1964. The Higgs boson, often called the God particle, a term coined by Leon Lederman in 1993, plays a key role in explaining why some particles have mass. However, the name has drawn criticism from some physicists for being misleading. The Higgs boson is a massive scalar particle with no spin, electric charge, or color charge. It interacts with the Higgs field, a fundamental force field that gives mass to particles through the Higgs mechanism. This interaction is essential to understanding why particles possess mass and how they interact. However, the Higgs boson is highly unstable and decays rapidly into other particles upon production. Due to its short lifespan, scientists cannot directly observe the Higgs boson. Instead, they study the particles produced when it decays, using detectors to track these decay products. If the observed pattern matches predictions based on the Higgs boson's properties, it suggests that the Higgs particle was indeed produced. However, since other collisions can produce similar decay patterns, researchers must analyze data from trillions of collisions to verify their findings. Additionally, to confirm the results, the same pattern must be observed by two different detectors, ensuring the findings are not random. Extensive research has also been conducted to investigate potential connections between the Higgs field and the theory of cosmic inflation, which explains the rapid expansion of space in the early universe. This connection could provide valuable insights into the origins and development of the cosmos.